Okay, welcome to lecture class meeting 12 of EECE574. The midterm will be taken next week from 7 p.m. to 10 p.m. in this class meeting room. And as you know, everything is open except any human assistance. Got it? Even you can use ChatGPT if you want. However, you cannot share, you cannot discuss with any human being. Got it? And our homework 9 is also assigned, mostly about Gaussian random variables and vectors. I found nothing to be corrected, and we are covering complex random variables and processes, and hopefully today we will start time average and ergodicity. Here goes the review. We studied some functions. So first, we define the Q function as the right tail probability of the standard Gaussian random variable. So we have 1 over square root 2 pi e to the negative y squared divided by 2 and dy. So if I visualize it, we have a centered standard Gaussian, and this is the y-axis, and here is our point x, and we compute this probability. Got it? So this is Q of x. Now, suppose we have two independent Gaussian random variables with mean 0. So here x is normal 0, 1. And here we have x1, x2 is real jointly Gaussian random variables with 0 mean vector and scaled the identity matrix as the covariance matrix. Now, what we are going to do, sorry, not necessarily this. Okay, let me a little bit modify. Oh, yeah. So let's say, is this. Mu x, mu1, and mu2. And here we have sigma square 0, 0, sigma square. So we assume that the Gaussian random variables x and y are independent and having the same variance, but the mean value can be different. And we define chi as the square root of mu1 square plus mu2 square. And as I told you, in order to define such a number, the mu1 and mu2 have the same unit if it is a physical quantity. Got it? You cannot add anything to having different units. Anyway, given that, what do we want to do? So here goes x1 axis and x2 axis, and we may have some mean vector mu. And what we want to do is, again, very similar. We want to find the tail probability. So we draw some circle, and we want to compute the probability that your x1 squared plus x2 squared is greater than or equal to some value r. Okay, and this can be written in terms of the Markham's Q function, as the first argument talks about the magnitude of this mean vector with respect to the variance, the standard deviation. So here goes chi divided by sigma, which determines the kind of scaling And then you have the number argument that corresponds to this x. By the way, for general, so I'd better not say this. For general Gaussian random variable following this distribution, if you want to compute x greater than or equal to r, then it becomes q of r minus mu divided by sigma. Okay, got it? So here goes kind of a constant that makes the argument unitless. Got it? So here, as you see, I assume the mu1 and mu2 and sigma have the same unit. So you have unitless quantity, unitless quantity. Got it? And now we have, in the third case, we have how many random variables? Yeah. N random variables that happens to be an even number, so 2m. Now, almost the same thing. So given x1, x2, dot, 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 up to 2m. So we have an even number. We have some mean vector, and we have scaled identity matrix as the covariance matrix. So these 2m Gaussian random variables are independent and having the same variance. And again, what you want to do is that if we define this as a random vector x, then what is it? X 2 norm square, sorry, 2 norm greater than or equal to r is written as written in terms of the generalized Markham's Q function, Q sub m, and here goes the same thing, chi divided by sigma and r divided by sigma. Ready? Here, a 2 norm vector is usually denoted by just ordinary norm if there is no confusion, and it's defined as what? X1 square plus dot 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 up to some xn squared. Ready? So you can see that the definition of Q function and the Markham's Q function and generalized Markham's Q function share the same idea. You draw a kind of circle, but in this case, there is no circle because we have one dimension. But all the other cases, we have circle, sphere, hypersphere that is centered at the origin, and we want to find a kind of tail probability. Got it? And they all share the same name Q. Got it? Nobody laughs because you've never seen the Star Trek TV series, and there appears a character called Q. But anyway, yeah. So we've covered this, and here goes. So these three quantities: Q function, Markham's Q function, generalized Markham's Q function. They are all loved by communication engineers, and today I'm going to talk more about that here when I talk about why we need complex random variables and processes. Now, statisticians love the first one, and it is slightly different, but almost same thing. So here we have again Gaussian random vector consisting of n random variables, and we have same thing, some mu vector, and here same sigma square times identity matrix as the covariance. The difference is that now we can have odd number n. Got it? So whenever we have complex number, it consists of two real numbers. That's why we have even numbers up to generalized Markham's Q function. And also the difference is that I don't know why, but the statisticians loved not 2 norm. They loved 2 norm square. Got it? So yeah, they defined chi-square distributions, and in special case, when mu is a zero vector, they call it central chi-square distributions of n degrees of freedom. If mu vector is not a zero vector, they call it non-central chi-square distribution of n degrees of freedom. As I told you, the difference is that they define y, for example, as the 2-norm square. So it's the sum of squared x1, x2, and xn. Got it? So you can easily link the generalized Markham's Q function and the chi-square distributions with even degrees of freedom. So that's the review. And we will quickly see some examples related to this independent Gaussian random variables having same variance, and then we'll move to the next topic. So here goes an interesting thing. The first question is this. So we have what? This notation is not that popular. So let's say Z is a complex Gaussian and proper. Here, the calligraphic letter Cn is quite often used to mean proper complex Gaussian. As I told you, the complex Gaussian random variable can be proper or improper, but usually complex normal means it's proper. So I really hate, but anyway. And given that you immediately have this figure in your mind, so it corresponds to two-dimensional real Gaussian random vector, and the mean is located at the origin. And what is the variance of the real part and the imaginary part? A sigma square. So real part has variance sigma square, and imaginary part has variance sigma square. Got it? So variance is defined as what? The z minus mean of z modulus squared. What does that mean? Real part squared plus imaginary part squared. And as I repeatedly told you, Gaussian proper means that they are independent and having the same variance. So if the variance of the complex Gaussian random variable is 2 sigma squared, then real and imaginary parts have half of the variance. Got it? So never forget that. And then you can easily convert it, if you want, to the PDF of the real and imaginary parts. Or you can use, in this case of 2 sigma square, something like this. If I remember correctly. Got it? So here, z is a complex number. And here goes the modulus squared of z that corresponds to x squared plus y squared. Got it? Now, given that, first question is find the probability of event that the real part of z is greater than or equal to some number a, real number a. And whenever you see this kind of algebraic expression, then you must immediately have what? So this is z plane, and you have a here, got it? And what is the area of your integration? This area. And due to the independence, real part of z is real Gaussian, right? So real Gaussian greater than some number. So you immediately use Q function. Since mean is 0, there is no subtraction of something here. So a divided by sigma, as you've seen repeatedly in the normalization for the Markham's Q function and generalized Markham's Q function. Now, the second case. Same figure, but a little bit different. What? The radius is B, and you want to compute the Z is realized in this region. So you use Markham's Q function. Got it? Since mean is 0, the first parameter is 0, and the second parameter is simply B divided by sigma. Got it? Now, since we've covered 1D complex Gaussian, now let's move to n-dimensional, capital N-dimensional complex Gaussian random vector. So probably you want to denote it as C of Cn, mu, and 2 sigma square I. The reason why I put it here, 2 sigma square, is that I want to just emphasize each real part has variance sigma square, and each imaginary part has variance sigma square. Now, what is this probability? So whenever you see some probability of event, right? What we do is 2 approaches. You just algebraically convert that event to an equivalent event. Second one is to immediately visualize what that means. So let's visualize and see what is that. Of course, since we have n-dimensional complex Gaussian random vector, we have to think in 2 n-dimensional real Euclidean space, which is impossible. So since this n can be anything, let's reduce it to 1. Then what does that mean? Whenever you see 2 numbers subtracted, as you learned in high school math, probably 4th semester of the 1st grade elementary student, what does that mean geometrically? For example, you have 5 minus 2, not algebraically, geometrically. What does that mean? You have a ruler, and you have what? 5 minus 2. From 2, you measure the length to 5, right? Same thing. So 5 minus 2 means that here you have 2, here you have 5. You measure this distance. And this idea extends to what? The subtraction of vector and subtraction of complex numbers. So here, these are not only vectors, but also complex vectors. But idea is same. So suppose this is complex, even though and it should be n-dimensional. Let's say mu is here, and let's say C is here. What does that mean? This one. This is the distance from mu to some z, right? So suppose this is some vector z, then this complex number means this vector, that complex vector. And this vector means this one. Now, what you do is that you compare the length of these 2 vectors and want to say that, okay, z is included in this event if this inequality is satisfied, which means that the z must be further from mu than c, right? So what you do is that you draw a straight line connecting mu and c and divide by 2, and then which area? Z must be further from mu. So that area? Am I right? I believe so, right? So depending on the location of 2 vectors c and mu, you may have quite different areas to be integrated. However, you have what? You have independent Gaussian density. So mu is what? So you have some mean mu. So this is the mean. And your spherical density function is centered here. And what happens now? So you have some contours of your complex Gaussian random vector, and you have a hyperplane that slices this apple or pear, right? And then you want to find how much probability is here. That is the geometrical interpretation of this event. And surprisingly, your algebraic manipulation will show that the result is simply can be written in terms of Q function. Not Markham's Q function, just the Q function, single Q function. Why? So let's follow this logic. So first, this event has some non-negative number greater than the other non-negative real number. So this event is equivalent to the next event where you have squared both sides, right? They are equivalent, right? And then by using the definition of the norm square over complex number vector, we expand that. But here, some of you may not remember. So let me give you an example. So given a complex number, what is modulus squared without using modulus operator notation? Yeah, that is z times z conjugate, or z conjugate times z, right? And now, suppose you have vector z, and now you want to compute the two-norm square. What is that? That is z Hermitian transpose z. Okay. So what they do is this one. So let's see the first term, z minus mu norm squared. Then what? This is z minus mu Hermitian transpose z minus mu. And then you expand by using the fact that this Hermitian transposition can be distributed. And then you expand to have what? First, you have z Hermitian z, then you have z Hermitian mu, you have mu Hermitian z, and then you have mu Hermitian mu. And you use this definition again, then the first term becomes the z vector norm squared, and the last term becomes mu vector norm squared. What about the cross terms? What about these two cross terms? So here goes another trick. Suppose you have some complex vector A, Hermitian transpose complex vector B, then what is this? This is a complex number, right? Because you have inner product. What about conjugating it? What happens if you conjugate? Then you can interpret this conjugation as Hermitian transposition, the special case Hermitian transposition. And then, as you learned in your linear algebra with transpositions, Hermitian transposition has the same property. What? B Hermitian A. Got it? As you have A, B transpose equals B transpose A transpose. Similarly, AB Hermitian transposition is B Hermitian transposition A Hermitian transposition. So here, the difference is that this is A and that is B. Got it? So what about the Z Hermitian mu and mu Hermitian Z? They are conjugate pairs. And what about what happens you have the Z plus its conjugate? That becomes 2 times the real part of z. Got it? And in this case, these are complex scalars, so 2 times, negative 2 times real part of, you can choose anything. If you want z Hermitian mu, or if you like mu Hermitian z, you use it. So the strange event that was what geometrically this hypersphere cut at the distance from mu by radius some number, exactly the half of the distance between mu and c. We have now what? We have now this one. You see, we just worked on the left-hand side. We do the same thing for the right-hand side. Then we have what? Z dome squared minus 2 times real part of the inner product plus norm of c squared, as I have written here more than 10 years ago. And then we cancel the first terms, right? And what about this? Real part of A plus real part of B, when A and B are complex numbers, are what? Real part of A plus B. So real part of A plus real part of B is simply real part of A plus B, right? So we can group this real part together, and what? We have, and also divide by 2 to eventually have real part of C minus mu. What does that mean geometrically? From mu, you go to C. So from mu, you go to C. So that vector, complex valued strange depth vector, inner producted by Z is greater than norm of C squared minus norm of mu squared divided by 2. Now, what is this, by the way? This is an linear transformation of Z. Inner product of a constant vector, inner product of constant vector and a complex Gaussian random vector becomes what? Complex Gaussian random variable, right? So this is what? This simply now a complex scalar. What? It's a proper complex Gaussian random variable. I didn't prove, but probably you remember that given a Gaussian random vector, any affine transformation is a Gaussian random vector. That includes the case where your matrix pre-multiplied to your Gaussian random vector can be a row vector. In that case, you have what? A scalar, right? Same thing happens. If you have a proper complex Gaussian random vector and you pre-multiply a complex vector, row vector, then the result is what? A proper complex Gaussian random variable. So this is simply a proper complex Gaussian random variable, and you must remember that any proper complex Gaussian random variable has what? Independent real part and imaginary part having the same variance. So circularity is given to you now. Now, real part is taken. What does that mean? You have something, right? You have something that is Gaussian and real part is taken. And if I draw for you, suppose this is complex plane and you have complex Gaussian random variable that has spherical, that is circularly symmetric density with respect to center, and then you take the real part. What? Then real part is simply real Gaussian. So what does that mean? This what it is? It's real Gaussian random variable. And this is real number. So you eventually have probability of real Gaussian greater than or equal to some real number. Then the answer is Q of something. And in order to find that something, you need to compute the mean of this Gaussian, real Gaussian random variable and variance of real Gaussian random variable. And here goes the computation and done. So you have eventually Q of something. And let's see what it is geometrically. So what it is. See that? The numerator is the distance between mu and c. The distance between mu and c. And what is sigma, by the way? By the way, you can interpret it as half the distance. So this distance, right? This distance is c minus mu divided by 2, right? And sigma is what? Actually, this complex Gaussian random vector has any component, real or imaginary or rotated version of that one. What? Having standard deviation sigma. That appears here. So any location of c and mu doesn't matter. What matters is only the distance between this c and mu. So remember this. This problem actually confused me a lot when I was the first year professor. Got it? And one of the Korean students who was not my advisee approached me and say, hey, professor, I have this problem which my advisor gave me to test me, and I have no idea, help me. So I helped him. And in the beginning, when I wrote up to this point, I said that it may involve generalized Markham's Q function. No, Q function. That was the surprise, actually. Got it? So if you have read it, I probably wrote somewhere. This is his name somewhere. Yeah, Baeksu's problem. His last name was Kwak, and Baeksu Kwak. I still remember him. Anyway, this is almost the same problem, right? You have now some non-scaled identity covariance matrix C. So this problem is much difficult. But what do you guess? So what would be the problem at the probability of this event given proper complex Gaussian with mean mu and some positive definite covariance matrix C? And surprise, surprise, still you have Q function. Okay? But it looks a little bit difficult, so you do it, okay? So you follow exactly the same idea, and you can have that result. And if you insist not working on that, then I will be putting that in the midterm exam so that you can study. Got it? So we are really done with that part. Oh, by the way, I promised to talk about more on other topics, which I didn't write. So yeah. So we have up to this point, and I haven't yet told you why we are concerned about complex and also Gaussian random variables, vectors, and processes. And here goes my answer. That is actually from our signals and systems and communications theory. So let me draw a figure. Suppose you are here, and your partner to get your information is far away. And you have only some medium that is vacuum or air between two persons. Is it UUM? Yeah. What do you do? Our human being have found that we can use so-called radio wave, right? And it has antenna, and the radios have some electrical systems that changes information to electrical signal. And then this radio actually radio is a communicator. It's not you say radio. It is actually not, okay? And this is converted to radio wave. And then it propagates through the medium. And then your receiver does what? It receives radio wave and converts it to electrical signal. And eventually, your information is recovered. But in order to convert an electrical signal to radio wave or vice versa, what do we use? We use so-called the antenna, okay? So this is RF antenna. And what is antenna? Antenna can be defined in many different ways, but current standard is this one. It's a conductor with some terminal, and the terminal has standardized connector. For example, suppose you have a dipole antenna, then what do you have? You have some connector here that can be BNC type or sometimes N type, sometimes SMA, but they are all have commonality in that it's connected to a cable, RF cable. And RF cable can be understood as what? Understood as a pipe with half filled by water, and you have some waves propagate through the pipe. And if this is the end connector, then what? There is some special coupler that changes this ripple to radio wave. Got it? And what is important here when it is this ripple electrical signal, so far electrical signal, and here the antenna radiates radio wave. What matters here is that since it has only two polarities, as we usually have a pair of wires in the electrical engineering, ground and some VCC or something. So what is important is that you observe the change of that ripple and converts to electrical field and magnetic field so that your information can be propagated through even through a vacuum. Got it? And people have found that in order to efficiently radiate electromagnetic wave, especially radio wave, the antenna size must be big enough. And antenna size, the rule of thumb is that this antenna size must be in almost the same order as the wavelengths of the radio wave you want to generate. For example, suppose your carrier frequency, that the radio wave has center frequency around 3 gigahertz. which means that 3 times 10 to the 9 oscillations per second. It's really amazing, right? Yeah, just within the 1 second interval, we have 3 times 10 to the 9 oscillations. Amazing. And it has what? 0.1 meters of wavelength. Sorry, 0.1 meters of wavelength. This around this. Okay. And our cell phone has center frequency around 3 gigahertz. If it is LTE, probably less than that. If it is 5G, slightly larger than that. So actually, our cell phone, this size, around 10 centimeters, is very good to efficiently radiate that range of radio wave. And some of you may wonder then, okay, then my AM radio, which my father and mother used when I was a kid, AM radio has what? Center frequency, some kilohertz. And your FM radio in Korea has center frequency around here. Then, okay, let me see, number is not beautiful. So let me just say that, okay, I have just 13 megahertz, okay? Just for simplicity. Then, how many times? 100 times, right? So 100 times difference of center frequency, which means that this one has lambda. So if center frequency is 30 megahertz, the lambda is what? 100 times, right? Which means that 10 meters. But you don't have 10-meter large antenna for your AM and FM radio. What happens? Actually, the radio stations use tremendous power to transmit very strong signal. And it propagates, and actually it is filled here. We do not feel at all, but the broadcast, AM broadcast and TV broadcast signals are filling this air, which is very strong, but actually it does not interact with our tissues, so we are okay. But anyway, what is important is that we need to generate a single real number, which is a function of time, whenever we have antennas, okay? So we can model this electrical signal that is fed as a real bandpass signal. So if we use Fourier transform, that this signal that is applied to the antenna is what? Having some conjugate symmetry. So let's say this signal is x of t, and the Fourier transform of it, which is defined as just the inner product between x and a complex sinusoidal function, is what? Since x is real, if this is real, that the continuous time Fourier transform has what? Complex conjugate symmetry. Which means that x of t is real if and only if its Fourier transform satisfies what? This property. If we evaluate Fourier transform at negative f, then x of f and x of negative f are conjugate pairs. So they have the same real part and the opposite imaginary part. Got it? And if you visualize this signal x of t, that looks what? Since this is real, it oscillates very fast, right? And if you count the number of zero crossings divided by 2 within a unit second, then it will be similar to your center frequency, right? So whenever we have radio communication, we have antenna that converts our signal generated by electrical system to a radio wave. That is antenna. And another antenna in the receiver part that converts the radio wave into an electrical signal so that your electrical equipment can process the signal, right? And each antenna has, right? Each antenna has its own corresponding real valued bandpass signal. This is very, very important, okay? You have, for each antenna, you have real valued bandpass signal. Now, so we are given a real bandpass signal which can be represented by some complex valued function x of f satisfying conjugate symmetry. Now, from here, this is quite strange, but very standardized trick. What we do is that we choose some nominal center frequency. We can choose any number, actually. We can choose any number close to this signal. If it is not necessarily be the center. We can choose any number, actually, mathematically. But usually, we try to find some number that can be called center frequency. But anyway, so we have two numbers, f1, fc, and negative fc. And then what happens? Under the assumption that most of the energy of this signal is grouped together around this fc and negative fc, we can eventually show that this x of t, blah, 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 and can be written in this form. Some complex valued signal. This is complex baseband signal. Be careful. This is what? Real bandpass signal. And this is complex baseband signal. And then you have complex sinusoidal signal that has the frequency which you have chosen. So what does that mean? Given x of t, if you choose different fc, you have different xc of t. Okay? Sometimes if you can put some theta here, then it has derotating theta there. Got it? And to prove this one, actually, it's not that difficult, but quite lengthy. But what is important is this one. So we are radio engineers, most of you. We have to deal with real bandpass signal anytime. And what does this equation mean? If you choose a center frequency, then there exists a complex baseband signal that satisfies this equality. So here you have some baseband spectrum here. Got it? So they are Fourier transform pairs, and they are Fourier transform pairs. Got it? So our communication engineers usually, after we kind of agree on what is the center frequency, we just work with a complex baseband signal. And this continues even when we have a noise here. Okay? So far, I just assumed that there is a signal. But sometimes we have a noise. So our signal consists of let's say, y of t, consists of a desired signal x of t plus noise. And here, since we are radio engineers, this is real bandpass signal. And this is could could be real bandpass. So here we have our signal, and there is some noise. Okay, I'm not going to talk too much about the white noise because we haven't yet studied the power spectrum. But anyway, we have a noise. And also, since Marconi's era, we have been using some special electrical system called bandpass filter in our radio in order to avoid any interference from other stations. So we assume that in the frequency domain, usually we have a bandpass filter that filters only the signal, desired signal, and also the noise or interference inside our intended band. Got it? So we can assume this noise is also a real bandpass noise signal with now uncertainty. What is that? What do we do with some signal with uncertainty? One approach, and which we learn in this course, is what? We model that one as a random process. So this is a real valued bandpass random process. But fortunately, there is no difference. Suppose we choose some nominal center frequency FC. Then what? We have corresponding some complex baseband random process n sub c of t times complex sinusoidal signal. So given a real valued bandpass random process, if we choose some center frequency, reasonable center frequency, then what? There exists a complex valued baseband random process that equates these two. Got it? And now, the last part. Suppose n of t is a Gaussian random process, especially Ysen stationary. Then my question is, what can we say about the corresponding complex baseband complex baseband random process NC of t? First, you can easily guess that this should be Gaussian, but complex Gaussian, right? So let me repeat. This is very, very important, okay? Suppose this n of t is a real valued bandpass, Ysen stationary Gaussian. You know that it's strict sense stationary, right? Because of what we have learned. Given that, my question is, what can we say about this equivalent complex baseband signal? By the way, there is a terminology like this. We say xc of t, that complex baseband signal, is the, actually is a complex baseband equivalent to x of t. Got it? So given a real valued bandpass signal x of t, this complex baseband signal is called a complex baseband equivalent. By the way, this is a noun, not adjective. Got it? Similarly, we say that this complex baseband random process is a complex baseband equivalent to n of t. So in terms of this complex baseband equivalent, let me ask you a question. What can you say to this complex baseband equivalent to the real bandpass Ysen stationary Gaussian random process? And our answer is, first, is complex Gaussian. And you can easily guess. And it's surprisingly, it's proper always. Okay? It's proper complex Gaussian. That's why, okay, that is one of the reasons why we repeatedly see proper complex Gaussian random variable vector processes in communications engineering and radar engineering too. Radar is what? Radio, right? Radar, that acronym is radio detection and ranging, right? They use radio wave. They use antennas. They use RF components. Very similar to radio communicators. Got it? And this part will come later, not today, okay? Because I want to cover it again when we cover power spectrum. Got it? And we have very long way to cover. But this is the most important, probably especially to freshman graduate students or sophomore graduate students. This is the most important thing you have to remember as a communication, especially radio communication engineer. Okay, I believe we are done, and we will be back after. See that I talked a lot about the power spectrum here for the Gaussian random process, so we will be back. You have to be patient. Okay, so I believe I have one more topic left before we move to ergodicity. That is the widely linear processing. So I'm very intrigued by this propriety and impropriety of complex baseband equivalent to communication signals when I became a professor. Okay, I had no idea when I was a graduate student actually, but after I became a professor, I had very much interest in that. And whenever I talk about complex something, many people just pissed it off, saying that, okay, suppose I have an n-dimensional complex number, let's say z, okay? Then it is what? It can be written as the real part and imaginary part that are real vectors. And so whenever I mentioned this propriety and impropriety, they said that, okay, Professor Cho, let me just put them together, which means that a real of z, an imaginary part of z, and we have what? R to the 2n. Then we are back to real domain. Done. Actually, that's logically true, okay? And this is one way. Another, there is, and by the way, given complex vector z, putting real part and imaginary part together and having a twice length vector, then this is called the real augmented. Just a second. Real, what was that? Is it real augment? Just a second. Oh, sorry, real composite vector. Okay. It's not standardized one, but real composite vector. Okay, so you can think of a real composite vector that is equivalent to a complex vector. That is the one approach. The other is very strange at the first glance. What you do is that you put z and z conjugate. And this one is called complex augmented vector. Why do people do this apparently strange thing? Why? In terms of x and y, the upper part is x plus jy, and the lower part is x minus jy, right? Now, what's the use of this? But there is a use. Suppose you build a filter that processes a complex vector. The simplest signal processing unit would be linear processor. So here goes linear filter that processes Z. And that will look like what? The output equals what? Let me draw. Okay, here goes Z. Okay, let's say output is W. Then linear means usually W equals some matrix, let me say F times Z, right? Of course, you may say that, depending on our task assigned to this filter, we may design some strange nonlinear function, right? However, as an electrical engineer, the first thing you have to try is what? Linear approach. So this makes sense. So suppose you want to find some matrix F that satisfies your criteria, saying, for example, okay, I've given a complex vector Z, and I'm comparing it with a complex desired vector D, and I want to minimize the mean squared error, and I want to find such matrix F, right? Then this matrix F is called what? Linear minimum mean squared error filters matrix, right? And what would be the next one? Of course, you may say that, okay, there should be some affine function. So you may say that, okay, here is my linear part, and I add some constant B, then I have W. So W equals sum Fz plus B, and we want to find F and B, blah, 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 right? What would be the next step? And you may say that, wait a minute, I may just use this real composite vector and process it. So here goes Z, and here is the converter that generates the real composite vector, and here goes some big G and generates some W. Here, be careful. If this has length n, what about this one? This has length 2n, right? This is the one approach. And what about this? Here you have Z, and here is a converter that has Z and Z conjugate. And then you have some H and W. You can prove, I'm just kind of scratch the surface today. You can easily prove that such a linear filter and such a linear filter has same degrees of freedom. Means that if you are given a single criteria, if this linear filter can achieve some performance, that filter can also achieve the same performance. However, this part is very important. Your linear filter may be inferior to these two filters. Got it? Now, it's now your choice. You may always work with real and imaginary part and do linear processing. Or you may work with complex augmented vector. And if you love this one, this filter is called widely linear filter. Got it? And this is called linear filter. So not always, but sometimes such a system gives you better performance, especially when Z is an improper complex random vector. Got it? So whenever you have impropriety, so you do not have vanishing pseudo covariance, then sometimes, not always, sometimes this type of widely linear receiver or filter that still has simplicity of linear filter, right? Performs much better. And you may say that, wait a minute, Professor Joe, you just mentioned that if we have real bandpass Wisen stationary Gaussian random process, its complex equivalent is proper Gaussian. But here is the important lesson. Man-made signal, not nature-made signal. The Gaussian noise is nature-made because whenever we have conductor, then we have electrons. And if the temperature is not 0 Kelvin, what happens? Electrons zeta, right? And whenever we have ohmic some material, whenever we have a flow, so we apply electrical field. And as you learned in high school math, if you have an electrical field and if you have electron, what happens? What's the motion of this one? Equal acceleration, right? But why do we have Ohm's law? Because this electron cannot move, cannot follow constant acceleration. It kind of moves and sometimes bumps into the grid and moves, bumps into the grid. And that motion, if it is translated as a current, what happens? Constant current, blip, constant current, blip, something like that. And there are many, many, many electrons in a conductor, antennas, wires, and then what happens? In a very low level, there is what? It's non-zero. There is a current. However, its net current is almost zero statistically because electrons are moving randomly. It's very similar to our idealized gas, right? In an idealized gas, you remember the equation PV equals nRT, right? Why there is no mass of each molecule. And given the temperature, they are moving, they are having thermal jitters, and those thermal jitters generate the pressure, right? And blah, blah, blah. And almost the same thing. So nature generates Gaussian random process, bandpass. That translates to proper complex Gaussian. However, man-made signals as radar signals and some communication signals, they are often better modeled as improper complex signal when you find complex baseband equivalent signal given the real bandpass signal. Got it? And that's why this approach is sometimes, not always, becomes very important. Got it? Okay, that's all for the day. And today also, I could not cover this time average and ergodicity, but we are really done here now. Okay, that's all for the day.